Welcome to today's ArXiv CS Digest for March 16, 2026. We received 825 new computer science papers today across 66 subfields. Let's dive into the top picks. Trend 1 of 5, LLM Reasoning, Ethics, and Search. This trend unifies research on advancing LLM reasoning, ethical alignment, and search capabilities, including their underlying mechanisms and evaluation. This cluster covers 224 papers. Representative work includes Horizon Math, measuring AI progress toward mathematical discovery with automatic verification, mechanistic origin of moral indifference in language models, and Code A1, adversarial evolving of Code LLM and Test LLM via reinforcement learning. Trend 2 of 5, Advanced Vision and Multimodal Generation. These papers unify advanced visual understanding with precise, controlled generation across diverse modalities like image, video, audio, and 3D. This cluster covers 203 papers. Representative work includes Mixture of Depths Attention, Look Before Acting, Enhancing Vision Foundation Representations for Vision Language Action Models, and Glyph Printer, Region Grouped Direct Preference Optimization for Glyph Accurate Visual Text Rendering. Trend 3 of 5, Robust ML for Scientific Applications. Developing robust and reliable machine learning methods to address complex challenges across diverse scientific and engineering applications. This cluster covers 192 papers. Representative work includes robust and computationally efficient linear contextual bandits under adversarial corruption and heavy-tailed noise, effective distillation to hybrid XLSTM architectures, and physics-informed neural systems for the simulation of EUV electromagnetic wave diffraction from a lithography mask. Trend 4 of 5, Privacy, Safety, and System Optimization. Research explores methods to ensure system privacy, safety, and optimal performance across diverse computational domains. This cluster covers 109 papers. Representative work includes Differential Privacy for Network Connectedness Indices, Optimizing Task Completion Time Updates using POMPs, and SemBench, a benchmark for semantic query processing engines. Trend 5 of 5, Autonomous Robotics and Manipulation. The trend unifies research on equipping autonomous robots with advanced perception, navigation, and manipulation capabilities for complex real-world scenarios. This cluster covers 97 papers. Representative work includes Towards Generalizable Robotic Manipulation in Dynamic Environments, HSML3R, Physics-in-the-Loop Reconstruction of Simulation-Ready Human-Scene Interactions, and Perception-Aware Autonomous Exploration in Feature-Limited Environments. Up next, our first paper out of 5, Concurrent Composition for Differentially Private Continual Mechanisms by Monika Hensinger and Salil Vadhan from Institute of Science and Technology, Austria. Let's break down its key contributions. This contribution introduces the first general framework for analyzing differential privacy against adaptive adversaries in continual mechanisms. It handles interleaved queries and dataset updates, providing a robust foundation for dynamic privacy. Up next, our second paper out of 5, Why AI Systems Don't Learn and What to Do About It, Lessons on Autonomous Learning from Cognitive Science by Emmanuel Depot and Jitendra Malik from FAIR at Meta. Let's break down its key contributions. This foundational system enables the model to acquire knowledge by passively observing the environment. It captures learning processes that do not involve direct interaction, forming a crucial basis for understanding. Up next, our third paper out of 5, Intervene Bench, Benchmarking LLMs for Intervention Reasoning and Causal Study Design in Real Social Systems by Xiaojie Shi and Jichao Chen from Fudan University. Let's break down its key contributions. Intervene Bench evaluates LLMs' intervention reasoning and causal study design in real social systems. It uses 744 peer-reviewed studies, requiring models to reason about policy interventions and identification assumptions without predefined causal graphs. Strides is a novel multi-agent framework proposed to address the limitations of state-of-the-art LLMs on the Intervene Bench. It significantly improves performance, enabling more robust intervention reasoning and causal study design. Up next, our fourth paper out of 5, Lost in Aggregation, on a fundamental expressivity limit of message-passing graph neural networks by Aaron Rosenbluth from RWTH Aachen University. Let's break down its key contributions. This contribution formally defines the sequential layers of message-passing graph neural networks, detailing message, aggregation, and combination functions. It establishes the precise computational model for their subsequent theoretical expressivity analysis. This contribution introduces a generic class of aggregation functions, encompassing most conceivable aggregations for MPGNNS. This provides a unified and comprehensive framework for analyzing the expressivity limits across diverse message-passing architectures. This contribution defines a final readout mechanism for graph-level tasks, aggregating final vertex values and applying a multi-layer perceptron. This completes the formal specification of MPGNNS, enabling comprehensive expressivity analysis for both node and graph-level problems. This contribution rigorously proves that MPGNNS utilizing the defined generic aggregations induce only a polynomial number of equivalence classes on all graphs. This establishes a fundamental expressivity limitation, highlighting their inherent weakness compared to graph isomorphism. Up next, our fifth paper out of 5, Neural Networks as Local-to-Global Computations by Vicente Bosca and Robert Grist from Department of Mathematics, University of Pennsylvania. Let's break down its key contributions. The framework demonstrates that the neural network's forward pass output is the unique harmonic extension of boundary data within the constructed cellular sheaf. This provides a novel mathematical interpretation of network computation. The paper introduces a sheaf heat equation that converges exponentially to the forward pass output, propagating information bidirectionally across layers. This contrasts with traditional unidirectional forward passes, offering new computational dynamics. The bidirectional information flow enabled by the sheaf heat equation facilitates new capabilities like pinned neurons for constraint imposition, training via local discrepancy minimization without a backward pass, and detailed per-edge diagnostics.